Welcome to EE Know-How. In this video, we will learn about what a capacitor is, what its capacitance is, reactance, and the current flowing through a capacitor. A capacitor is an electronic component that is used to store charge in a circuit. And schematically, it's represented like this. The two terminals, X and Y, and with the capacitance C. Now if you look at the representation, it looks like an open circuit. And that is really what it is. A capacitor is nothing but two plates of conducting material that are separated by a distance in between them. So you have the two plates of conducting material, and this is X and this is Y, and the cross-sectional area is A for both the plates. And now these are separated by a distance D. The two plates are separated by a distance D, and in between the two plates it could be either just vacuum or any non-conducting material. So which is an insulating material really. So insulating material. So it's really, you have the two sides of the circuit, and then you have the two plates, and then there is an insulating material in between. So what happens, how this works, how the capacitor works, is what we are going to look at. Now if we hook up this capacitor in a circuit to a battery or a voltage source V, plus minus a DC source for example, and then we close the circuit. So what happens is there is a positive charge that accumulates on the plate X, and to balance that positive charge on the plate X, a negative charge accumulates on the plate Y. So it looks as if there is a current flow through the circuit initially. So a current flows to build up the positive charge on the plate X, and there is a current, basically that this is the whole current or the positive current, whereas really the electrons go this way and accumulate on the plate Y. So what happens is initially there is a current, but if this is a DC voltage source we are talking about, initially there will be a surge of current which will charge up the capacitor, and then there would not be any current anymore. So it's a DC voltage, so there would not be any current anymore. Now a charge is stored across the capacitor. So that charge is Q, which is stored across the capacitor, which is equal to the capacitance of the capacitor multiplied by the voltage across the plates. So now in this case the voltage across the plates is V, a DC voltage, and C is the capacitance, and Q is the charge that is stored across this capacitor. Now we would like to know what is C and what does it depend upon. So C is directly proportional to the cross-sectional area of the plates, and C is inversely proportional to the distance between the plates. So C is written as the proportionality constant, you put epsilon A over D. This epsilon is the permittivity of the material. This is the permittivity of the material that is in between the two plates. And now epsilon is epsilon r multiplied by epsilon naught, whereas epsilon r is called the relative permittivity, or it's also commonly known as dielectric constant. And epsilon naught is the permittivity of vacuum, which is a constant, and you can write epsilon naught is, if you look at physics textbooks, you'll see that 8.854 multiplied by 10 power minus 12 farads per meter. So that is epsilon naught is 8.854 10 power 12 farads per meter. Now the relative permittivity is what decides how much capacitance is there, and then depending on what is the material between the two plates, you will have different capacitance here. So now let's look at, say, for example, in semiconductors, you usually have capacitances with the dielectric in between them is silicon dioxide. And it has an epsilon r of around 3.9 for silicon dioxide. Now next let's look at the current flowing through a capacitor. So now, like we said before, when you apply a voltage V across a capacitor and there is a resistance, series resistance, it could be the source resistance, and now you close the switch here, you apply voltage V across the capacitor, there will be an initial surge of current. So you cannot, now capacitor does not have any DC current I like we saw in a resistor. It has only an AC current I of t, which varies with the time, and then it dies down if you apply a DC voltage here. So now the current I of t in a capacitor is written as C times dV of t over dt. So only when there is a change of voltage across the capacitor plates, there is current. So only when the Vc of t changes, there is current flowing through the capacitor. Really, if you look at it, there is no real current that flows through dielectric, because in between the two plates is basically a dielectric. So it's non-conductive material. So how does the current flow in a capacitor? If you look at that, it's basically the current to charge up the plates, the top plate and the bottom plate. So you put positive charge on the top plate and negative charge accumulates on the bottom plates. And if you put positive on the bottom plate, negative charge accumulates on the top plate. So that current actually really does not flow through a capacitor, but to the plates of the capacitor. So only when the voltage change, there is a current flowing through the capacitor. Now, if you want to see what kind of resistance the capacitor has, you cannot really call it a resistance now. It is a kind of an imaginary quantity, and it is called reactance. And like we said, the reactance of a capacitor depends on the frequency or the voltage change with respect to time across the capacitor. So now for a DC voltage, so ideally once the plates are charged, there is no change in the voltage across the capacitor. IC would be 0. There is no current flowing through the capacitor. So this reactance of a capacitor is X of C is minus J over omega C, where omega is the angular frequency, so you can write it as minus J over 2 pi F C, which is also written as 1 over S C. So that is the reactance of the capacitor. Now let's see what the units of capacitance are. We have written Q, which is charge, is C times V, and C is Q over V. Now the units of C are coulombs, the units of charge over voltage, and these is farads. And farad is a huge quantity, so usually capacitances are measured in microfarads, which is basically a farad multiplied by 1 to 10 power minus 6, or sometimes nanofarads, and picofarads, which is farad multiplied by 10 power minus 9, or farad multiplied by 10 power minus